Okay, welcome to my next little presentation here. Today's is going to be a talk about some history of optics. And this is in fact one of the oldest, more popular science seminars that I've ever written. And it's about some interesting forgotten experiments that have been done in the history of optics through literally hundreds and hundreds of years. So one little bit of personal historical note. This talk was, as I said, one of my first popular science lectures I ever sort of did, and it was really inspired by my PhD advisor, Emil Wolf, because Professor Wolf was also a big fan of the history of science, and he gave for many, many years a lecture series, or actually just a lecture that he gave at multiple places called Scientists Who Created the World of Optics. And that's me with Professor Wolf, both when I was a master's student and getting my PhD. But his lecture was really well received, and he talked about the lives and the accomplishments of a lot of scientists. When I started blogging about the history of science, I started finding all these other experiments that people had done that had been left sort of no longer talked about that much by physicists, at least. I thought it'd be fun to talk about them and the people who did them. So really, there's a number of reasons to talk about such things, one of which is just I like to say overall that history is important. It's important to understand where things came from, because if you look at historical experiments properly, it can give you crucial context and understanding of how science is done. And there's been so many important and enlightening experiments that have been forgotten by science. And this isn't really a criticism of science. I mean, most scientists are not in the business of reading every little bit of history of their field, but you can learn a lot by looking at some of these old experiments. And among other things, they can really provide some inspiration, and they can also provide a better understanding of the philosophy of science, of why we do the things the way we do them, and how science is done. So, to set some of the stage here, I like to divide up the history of optics, and optics is really the study of light as a whole. That's my sort of general definition of optics, is the study of light. And we can really break it down into some broad periods. And the first period is really prehistory. The initial studies of optics and vision before there was really any science per se. There wasn't really any continuity of scientific discovery, at least not in the way we think of today. And that all changed around the year 1700, and I'll talk about why, when really optics started to be treated as on a more physical basis, and people interpreted light as a stream of particles traveling through space. And that view held up until just after the year 1800, when it was discovered that light can really be treated as a continuous wave, like a water wave or a sound wave. And then almost 100 years after that, and it's sort of fascinating how the major revelations in optics really came at 100-year intervals. The quantum era in the early 1900s recognized that light actually acts both as a wave and as a particle. And if you skip ahead actually another 100 years, in the modern era, we've really started to recognize that light can be even weirder than we imagined. And I draw the modern era somewhere around the 1960s, though I'll also mention that around the year 2000, there were some other major changes in the field of optics. Well, who did what to make these periods of optical history? Well, the prehistory, as I like to call it, is really all the venerable old scholars, Aristotle, Ptolemy, and one we'll talk about today, Ibn al-Haytham. The particle era started when Isaac Newton published his text Optics in 1704. The wave era really started when Young published the results of his famous double slit experiment in 1803. The quantum era started formally. Of course, these things are not sharp boundaries, but there were a lot of discoveries leading up to the main ones that we talk about, and then there were others past it. But the quantum era you could really mark by Einstein publishing his explanation of the photoelectric effect in 1905. And what I usually call the modern era started when Theodore Maiman built the first laser in 1960. And with the invention of the laser, suddenly there were all these other parts of optics we could study that were previously really impossible to study. Well, what about forgotten experiments? The ones I want to tell you about are not the famous experiments, so I'll touch upon each of them in turn, but really want to touch on some experiments that people know less about. In the prehistory era, I want to talk about Ibn al-Haytham in his book of optics that was written around the year 1011. So that falls into the prehistory category. Now, then we'll skip ahead to the particle wave boundary, somewhere in that era when the particle theory was ending and the wave theory was coming up. And that experiment I want to talk about there is François Arago, a French physicist studying the phenomenon of stellar aberration. Then right around the wave quantum boundary, there's an experiment by Charles Barkla that showed that X-rays have polarization. And that was done in 1905. And then finally in the modern era, soon after the laser was created, Leonard Mandel showed multiphoton interference, or so it seemed, in 1963. And those are the 4 experiments I want to touch on in detail. So let's talk a bit about the prehistory of optics. When you look at the earliest scientific studies of light, which was really people seriously asking the question, what is light? And how is it, where does it come from? What does it mean? That can be attributed to people like Aristotle, Ptolemy, and Euclid, who really did the first theoretical musings on the subject. And back in the day, light and vision were concepts that were kind of independent, though they were intertwined. That is, people didn't necessarily think, as we know now, that vision is really the measurement of light. And in fact, you could see there were a number of different models of how vision actually works. And not all of them necessarily involved light by itself. Aristotle said that vision is affected by a form which comes from the visible object to the eye. So somehow there was no theory of imaging back then, so it was really the idea that somehow the structure of the object, its form, gets transmitted to the eye. And that's at least close to the way we understand it now. But there were also people like Ptolemy and Euclid who had the reverse view. They thought that vision started with the eye itself and essentially projected. There was a ray that was projected from the eye that interacted with the visible object. And it's worth noting that there were other variations on these models as well. These are sort of, I would say, I kind of, as a simple example, say these are the main models of vision that existed. One that something comes to the eye, and the other something goes from the eye. But there were variations on these. And into this came Ibn al-Haytham, who we don't have as much information about him as we would like. But he was born in Basra, Iraq, and he devoted his early life to theology. But as I understand it, he basically became frustrated with theology because people were constantly arguing about the meaning of things, but nobody would ever come to a conclusion. You could argue forever. And in fact, we still do argue about theology to this day. And he became frustrated with the fact that nobody could basically come to a conclusion. But as a young man, he discovered the works of Aristotle and was really inspired to devote his life to the study of the physical world. And he studied and eventually commented on the works of Aristotle, Euclid, Archimedes, and Ptolemy, and really basically helped convey their thoughts to future scholars as well. Now, a bunch of his history is a bit unclear because there weren't very good records kept. There weren't systematic records like we have today. It's one of the frustrating things for someone like me, who's an amateur historian going back into that sort of pre-Newton era, is trying to separate fact from fiction and just understand what was really going on. But what we know of Ibn al-Haytham is he appointed a vizier in the Basra government. But it seems like he was dismissed from that job by either feigned or actual mental illness. He may have been struggling with a mental illness, or he may have just been trying to get out of the work because it was boring. Incredibly, he wrote possibly more than 200 works in his lifetime, and only 50 of those are still surviving in some form. He's often remembered for writing a clear description of a scientific method. He wasn't the first person to elucidate a scientific method, but he wrote perhaps one of the clearest that had been done to date at the time, of trying to say this is how we study the natural world. And he really studied a lot of the natural world. He studied optics, astronomy, geometry, mechanics, water clocks, medicine, anatomy, business, arithmetic, even civil engineering. Now, he was really a product of his time, as so many scientists are, and Ibn al-Haytham came about in an era that's often called the Islamic Renaissance, that the Islamic world was really undergoing this intellectual renaissance where people were free to study a lot of things and were very interested in the natural world, as well as the works of the ancient Greeks. So that work of Aristotle, Plato, and the rest, the Muslim scholars really carefully studied these works, and there were many translations made, and a lot of those translations helped to convey that information to future scholars, like Ibn al-Haytham did. And the so-called famed House of Wisdom was founded in Iraq around 813 CE. And some of the achievements that we have kept to this day from the Islamic Renaissance are Arabic numerals, which were done by al-Khwarizmi in 825. And al-Khwarizmi also introduced algebra to the Muslim world and then eventually to everyone, al-Jabr, which a lot of students, of course, are not very thankful for, but I am as a physicist. Well, what happened in about 1010 CE, Ibn al-Haytham was called to Cairo by the so-called mad Caliph al-Hakim. And that's another thing, we don't really know whether he was mad or not, or that was just name calling that was done to him. And he was called to Cairo because they wanted to dam the Nile. And eventually that damming of the Nile did happen with the Aswan High Dam. And Ibn al-Haytham was convinced he could do this project. He thought he could do that project, though when he arrived in Cairo, he concluded that it was not a feasible thing to do, which could have put him in a lot of trouble if the Caliph was truly mad. But it seems like he was given a government post anyway, though accounts vary, but it seems like he got a job in Cairo in the government. But soon after that, the records say that his mental illness came back, or again, perhaps he was faking it in order to get out of government duties, like modern day jury duty, trying to get out of it by saying some outrageous stuff to the judge. And as from what I've read, it's not clear whether he really was mentally ill one time or two times, and there was a duplicate story, or of course not at all because he was faking it. But in this case, he was put under house arrest in Cairo for 10 years and deprived of his belongings. Apparently, if he was just trying to get out of work, it didn't work this time, and he was imprisoned. And it was during this period that he developed his Book of Optics. And the Book of Optics is a really amazing document, a 7-volume book on vision, the anatomy of the eye, and studies of light propagation, reflection, and refraction. And one big thing that he did was provide numerous tests of what we call today rectilinear propagation of light. We take it for granted these days that when light is traveling in a uniform medium, that it just travels in straight lines. But Ibn al-Haytham provided numerous experimental tests of this and showed that really that to the best of his measurement at that time, light travels in straight lines from the object where it is created to the eye itself. And this also allowed him to advance a theory of vision where he really made that strong connection between light and vision. And a translated version of some of his words are, sight does not perceive any visible object unless there exists in the object some light, which the object possesses of itself or which radiates upon it from another object. So he was really saying, hey, you don't see anything unless light hits that object and then comes to your eye. So al-Haytham properly noted the now seemingly obvious connection between light and vision. He correctly surmised that the brain is the center of vision, not the eye. He had no real way of testing this, but correctly deduced that the brain was the thing that was actually figuring out what we're seeing. And he also stressed the distinction between primary and secondary sources, which is actually a big deal in optics to this day. The distinction between objects that themselves emit light and secondary sources, which are those things, for instance, when light shines upon another object and reflects light, that's what we call a secondary source. And for our purposes, he performed the first systematic studies of the camera obscura. Now, the word camera kind of gives it away, but if you're not familiar with what a camera obscura is, it's basically a pinhole in a darkened box. If you have a very small hole in a darkened box, you will get an inverted image of whatever is outside that box. So for instance, you have a tree outside, the light comes through, and because the light travels in straight lines, light from the top of the tree is going to go straight down and project an image that's going to be at the bottom of the image, and the base of the tree will be at the top of the image. And so you get an image of an object just through a pinhole. Of course, people make actual photographic cameras this way, pinhole cameras. And our modern day terminology of camera comes from this idea that you use a camera obscura and you put some film of some sort in the back to record the actual image you get. And using this sort of geometrical optics, you can demonstrate that you're going to get this reversed image because the hole is very small. Because the hole is small, all the light rays that are going to form the image have to pass through the hole, which gives it its image forming capabilities. And naturalists prior to al-Haytham had observed this effect via, for instance, sunlight traveling through gaps in leaves. And here's an image of a partial solar eclipse, and the gaps in the leaves during the solar eclipse, you no longer just see bright spots at the gaps, you actually see images of the solar eclipse itself everywhere that light gets through those tiny gaps. And this was observed all the way back to the era of Aristotle and so forth, but apparently nobody had studied this phenomena systematically to say, okay, what's really going on here? And al-Haytham's sort of famous experiment on the camera obscura was using multiple light sources to demonstrate that light followed straight lines through the holes. So, for instance, he had 3 candles, and he could block one and he could see 3 images from those 3 candles, and he was able to say block one candle and then see that the image on the other side disappeared. And so he was able to demonstrate the inverted image that arose when light passed through the holes. And people have speculated that Ibn al-Haytham, in house arrest, stuck in his home for 10 years, just had, light streaming through small gaps in the windows, and he was watching the light streaming through the gaps in the window shades, and that got him thinking about things like this camera obscura. We'll almost certainly never know, but it's a really romantic notion. And this was sort of a really beautiful early systematic experiment into how images form, how we actually see things that from the light that's emitted from objects. Now, the interesting thing about Ibn al-Haytham's experiment is it was actually done to prove a rather more important point about light than just the imaging properties. He wanted to show that light rays don't interact with each other. And this is something we know now in physics, that we tend to say that photons, or the particles of light, don't really directly interact with each other, that light beams pass through each other and as if they're not there. I mean, if you shine two flashlights and you intersect the paths of the flashlights, those paths don't get distorted. The light beams don't interact. And that was what Ibn al-Haytham wanted to show. He said all the lights that appear in the dark place have reached it through the aperture alone. And he said if the lights blended in the atmosphere, the lights of the lamps meeting at the aperture would have mixed in the air at the aperture, and they would have come out so mingled together that they would not be subsequently distinguishable. So he really said, hey, if light was interacting with itself, then when we tried to get all those different light signals to pass through that tiny hole, then we would have expected them to get distorted or be influenced when they came out the other side, but we don't see that. So this is one of the first experimental tests to try and show that light doesn't interact with itself. Now, from a modern perspective, it was not a very conclusive test, but it was still nevertheless a very beautiful attempt using the methods and tools he had available at that time in history and while under house arrest. But his work had a lot of influence. It remained one of the most influential optics books throughout that prehistorical period, and it was eventually translated into Latin. Al-Haytham was Latinized to al-Hazan or al-Hasan, and it influenced significant medieval optical researchers such as Roger Bacon, who one of these days I will have to say more about. So that's our first experiment to talk about, and that really covers a lot of the work up to the year 1700. And, well, to cover a little bit before that, by the late 1600s, the basic laws of what we now call geometrical optics had been established. Snell's law was really, well, it was known for a long time before that, but Snell himself formalized it in 1621, and the French philosopher Fermat established the so-called principle of least time in 1662. The principle of least time, another topic I need to come back to, is really the idea that light takes the path that takes the least amount of time in any situation. So in any situation, you can say, you can look at 2 points and say, what path does light take from point A to point B? And the answer is it takes whatever path takes the least amount of time. There are more refinements that can be done from that statement, but it was a big part of early optics, and it led the way to some more advanced physics. However, there was a big argument in the 1600s or in the late 1600s about the nature of light, because some people said light really acts like it's a wave. And Christian Huygens, a Dutch scientist, published Traité de la Lumière in 1690, suggesting that light is a wave. But other people were convinced that light is a stream of particles. And Newton finally published in 1704 his optics book. And his optics was an experimental whirlwind and masterpiece that really cemented the so-called corpuscular or particle theory of light for the next 100 years. But, and I probably should add an experiment in the particle era, but let's transition right to the wave era, because that's when things get interesting. So Newton's results were so impressive that people really didn't question them seriously for about 100 years. But in 1803, Thomas Young published his famous double-slit experiment demonstrating the wave nature of light. Basically, he said, shined light through 2 pinholes of very small size, closely spaced together, and when he set up the experiment just right, he could see interference patterns of the light coming through the 2 pinholes. And the only way to explain that adequately was by assuming that light is a wave. But surprisingly, Thomas Young's results didn't really gain broad acceptance right away. People still argued. But there was another phenomenon that came along that really caused people a lot of headaches, and that was the phenomenon of diffraction. Though light most of the time appears to travel in straight lines, people had noticed that when light goes through a very small hole with a sharp edge, or interacts at a corner, you shine light on a very sharp corner, that some of the light seems to bend around that corner. And nobody could explain how diffraction works based on Newton's corpuscular theory. So in 1818, the Paris Academy, they like to give out prize questions. They said, hey, we'll give you an award if you can answer this question. In 1818, they put out the question, said, hey, who can explain diffraction to us? Well, in that year, Augustin Jean Fresnel, another French scientist, said, hey, I can explain diffraction based on a wave theory of light. And another French scientist, Poisson, said, no, Fresnel's theory is nonsense, because if Fresnel's theory was true, you should be able to shine light on an opaque disk, a circular disk. And on the dark side of the disk, you should see a bright line appear right in that shadow region behind that disk. So Poisson sort of argued that, well, this theory is nonsense because you'd expect to see a bright spot, and who would expect to see a bright spot? And one other French physicist, François Arago, then did the experiment and found that spot, which is now called the Arago spot. And Arago is the subject of our next forgotten scientific experiment. He was a really amazing guy. He was a French physicist, mathematician, astronomer, politician, and as it turns out, an unwilling adventurer. And I want to share a link to a blog post I've written about his adventures, but I'll summarize them here in a moment. He made fundamental contributions to optics, the Arago spot we just mentioned, also what are called the Fresnel-Arago laws, and the stellar aberration theory I'm going to mention in a moment. And he did his work until about the 1830s. And then he went into politics and became an active liberal Republican in French politics. And he ended up guiding and influencing a lot of other scientists and spurred many other scientific discoveries. Now, the adventure part of his life is wonderful. He ended up going to Spain in 1806 to perform meridional measurements, to try and measure basically the shape of the Earth. Well, in 1808, France declared war and invaded Spain. And then all those Spaniards were really upset, and they started to wonder why there were these French scientists hiding up at the top of mountains, shining light signals back and forth between mountains. So in 1808, in June, Arago was accused of being a spy, and a mob tried to come get him, and he managed to dodge the mob by basically seeking voluntary imprisonment, and he was imprisoned in a fortress. Once he was in that fortress, he ended up reading the news of his own execution as if it had already happened. He read a newspaper account that said Arago went to his death nobly, and, well, basically reading between the lines there, he managed to escape prison. He escaped in a fishing boat, reached Algiers in August. In mid-August, he sailed to France, but while he was sailing to France, his ship was captured by a Spanish corsair, and he was imprisoned in Spain until November. There's a great story there, too. But freed from Spain, he ended up trying to take a ship to Marseille. Basically, he got freed by the Spanish because the Algerians protested the capture of their ship. But he tried to take a ship to Marseille, and a bad storm blew him back to the coast of Africa. It started to take on kind of the story of Odysseus here, an odyssey of trying to get home where he could never make it home. And he was blown back to the coast of Africa, at which point he just said, the heck with it, I'm going to take a dangerous 6-month overland trip back to Algiers. And finally, he managed to sail back to Marseille, where he was then put under quarantine for a number of weeks. And at the end of it, finally got to reunited with his family, who thought he was dead at all that time. And not only that, but he brought his scientific measurements with him through that entire trip. And bringing those measurements back after all that time and all that turmoil made him a scientific hero. He was still very young, but he was sort of made a national hero, and therefore was sort of given free rein to study any sort of scientific subject he wanted to. And he became very interested in light. And one thing that was of great interest in that era was the speed of light and the motion of light in the cosmos. Now, the speed of light itself was first measured by a fellow named Romer in 1676. And one of Romer's original figures is here on the left. And this was a really ingenious experiment because Romer recognized that the Earth, of course, is circling around the sun, and the moon of Jupiter is circling around Jupiter. But at some points in the motion, when the Earth is moving away from Jupiter, the light is taking a longer period of time to get to the Earth because the Earth is moving away. And when the Earth is moving towards Jupiter, we're running towards the light, so the light is coming quicker. So Romer recognized that the period of Jupiter's moon Io, the amount of time it takes for Io to make an orbit, should seem like it takes longer when we're moving away from Jupiter, and it should seem like it takes a shorter amount of time when we're moving towards Jupiter. And this is effectively a very simple version of the Doppler effect in physics. And with that knowledge and doing some calculations, he was able to make a measurement of the speed of light based on how much the apparent period of Io's orbit changed. Well, once people recognized that the speed of light was finite, this led to a number of interesting consequences. One of these is that the combination of the finite speed of light and the motion of the Earth leads to a phenomenon called stellar aberration. And basically what stellar aberration is that starlight and sunlight, though we don't really notice the sunlight, but starlight appears to come from different directions at different times of the year. Now, if we could measure this for the sun, the way this would work is as follows. If the Earth is moving to the left in my picture, then from the point of view of the sun, from the fixed point of view of the sunlight is moving straight down. But since some Earth is running into that sunlight, from the point of view of the Earth, the sun is moving to the right, and the sunlight is coming at an angle. Now, you actually experience this. You can actually experience this somewhat in your day-to-day life. If you're walking in the rain or running in the rain with an umbrella, as you're running, the rain appears to be coming towards you. So you have to tilt your umbrella forward a little bit to anticipate that the rain is kind of coming at you from an angle. But from a ground stationary point of view, the rain is falling straight down. It's just the fact that you're moving that makes it appear that it's coming at an angle. And this idea of stellar aberration, that you would see starlight come from different directions, slightly different directions based on the time of year, was first observed by James Bradley in 1725. Now, I have a little bit of math here, but we don't really need to worry about it too much. But basically what it comes down to is the angle theta at which the change of the light apparently seems to be coming from depends on the speed of light c and the speed of the object, like the Earth, that's moving. So in principle, you can measure the speed of light using stellar aberration. If you know how fast, for instance, the Earth is moving, and you measure how much the direction changes that the starlight seems to change, you can deduce the speed of light from it. But we already kind of knew the speed of light, and something that people were really interested in instead was variations in the speed of light. In that era, nobody knew that the speed of light was apparently constant for everybody. Einstein's special theory of relativity didn't exist yet, so it's natural to expect that the speed of light should be different based on the circumstances. Now, interestingly, in particular, in that era, people really expected that bigger stars should produce slower light in the corpuscular theory. If you think about shooting something up, well, let me put it this way. Heavier stars have a heavier gravitational pull. So light being emitted from heavier stars essentially has to climb uphill more in order to get moving, to get free of that star. You could think of it as having to climb a steeper slope. You know, if you ride a bicycle, if you go up a shallow slope, you can use, if you get a good running start and you go up a small slope, you still have a bit of speed when you reach the top of the slope. If you go up a taller slope, you have much less speed when you reach the top. So people wanted to measure these differences. They thought, okay, bigger stars, the light should be slower. But the phenomenon of stellar aberration alone was not precise enough to measure the difference. This formula at the top here, in principle, you could measure those differences in C from different stars, but this is not a precise formula to do it. Now here, and you can ignore the formulas for the most part, what people decided here was they recognized that if you use Newton's theory of refraction, remember this is in the era when people still believed that Newton was probably correct. They thought Newton's particle theory of light was correct. And how did Newton explain refraction? Refraction is the phenomenon by which light goes from one medium to another. It changes direction. If it goes from air to water, for instance, the direction of the light changes and it bends more towards the vertical. Well, in Newton's theory of refraction, he explained this bending of the direction by saying that the light must speed up. It must become faster in this perpendicular direction, in this what I call the z direction here. You can imagine that this interface represents a very steep hill, and as the light comes across and it goes downhill, it's suddenly moving faster in this vertical direction. It keeps the same speed in the horizontal direction, so overall its direction changes. Well, long story short, Arago realized that if light is traveling at different speeds, then that overall law of refraction must be different for light with different speeds. So if we look at different stars, we would expect that the heavier stars where the speed of light is slower and the smaller stars where the speed of light is faster should experience different amounts of refraction according to the Newton theory. So he set up a very simple experiment, and I drew this picture based on roughly what he describes. Back in that era, people didn't really provide good experimental figures, but he basically had a telescope that he'd pointed a star. He put a prism on one side of the telescope, or one half of the objective lens, and the other half he just let be undeflected starlight. And then he measured how much the light got deflected by refraction. And in principle then, this method would be much more sensitive to measuring slight variations in the speed of light. But incredibly, at least for Arago, he found that no matter what star he looked at, the light was refracted by exactly the same amount. That he could find no difference in speed regardless of whether light was coming from a big star or a small star. And as he put it, this result seems to be, with the first aspect, in manifest contradiction with the Newtonian theory of the refraction. Since a real inequality in the speed of the rays, however, does not cause any inequality in the deviations which they test. However, he came up with an explanation for it. It even seems that one can return to it reason only by supposing that the luminous elements emit rays with all kinds of speeds, provided that it is also admitted that these rays are visible only when their speeds lie within different limits. So basically what he said is, okay, the light that comes out of a star doesn't just have one speed, it has a whole range of speeds. And then our eyes can only detect those rays that have a very specific speed. So he basically was saying we can only detect those rays that have the same speed. Well, that turned out to be not correct, because, as we will note in a moment. But so to some extent, Newton's particle theory really didn't explain the theory. And a wave theory of light seemed like the only possibility. But this was also a problem, because in the wave theory of light, you would really expect to see a lot of variations in the speed of light based on the motion of objects. If the Earth is moving, we would expect the speed of light to be different based on whether we're moving towards the light source or away from the light source, according to the theory of the time. But in 1818, Augustin Jean Fresnel, who we mentioned earlier, suggested that, well, this light, if it's a wave, has to travel in some sort of material. We'll call that material the ether. And suppose that that ether gets dragged along with a material medium. So the Earth drags the ether with it so that you don't detect any differences in the speed of light because that medium is being pulled along with the Earth. It's somewhat ironic that Arago saved Fresnel's theory back in the day because Arago measured the Fresnel spot, and then Fresnel, in turn, sort of saved Arago's experiment by introducing this, what we could now call ether dragging. Well, when Fresnel explained this, that allowed Arago to embrace the wave theory of light. And in fact, this result also led to widespread belief in this idea of an ether, that light waves travel in some material medium that we can't detect. Well, it turned out that's wrong, because the true explanation of Arago's results lie in special relativity, Einstein's theory of 1905 that suggests that the speed of light is constant for all observers, and you don't need any ether at all. The idea of an ether has been completely discarded at this point because Einstein's theory really just says that the constancy of the speed of light is basically a fundamental part of the laws of physics. But this makes Arago's experiment very ironic, because it turns out it was a failed experiment. He didn't find what he was looking for, based on incorrect theories of light propagation, based on Newton's theory. It was interpreted incorrectly by Fresnel, who tried to explain it with the ether, but nevertheless, this whole thing, based on a lot of wrong ideas, helped convince people of the correct wave theory of light. And I just love the irony of that whole situation. Well, so that led into the wave era of light, and a number of things came about in that era. Fresnel and Arago together, in fact, in 1816, showed that there was a phenomenon called polarization of light, and they showed that orthogonal polarizations would not interfere. And this was interpreted by Young in 1817, that light is a transverse wave. Basically, if the light wave is moving in the x direction, then the light wave can be wiggling in the y direction or the z direction. It never wiggles in the x direction. That's what we mean by transverse. It's like a string. You tie one end of a string to a post and you hold the other end of that string and you wiggle it up and down or left and right. Those are the two polarizations of the string. Well, these were key results to determining the nature of light. What is light exactly? Well, Ørsted, Ampere, and Faraday, some other scientists we'll talk about another time, showed that electricity and magnetism are related. Previously, people had thought electricity and magnetism are two separate phenomena, but those three researchers showed that electricity and magnetism are related, and it was up to James Clerk Maxwell in 1864, building on those results, who kind of filled in a missing piece and said, hey, when we're talking about light, electricity, and magnetism, those are all essentially the same thing. That what we call light is actually an electromagnetic wave. It's actually an oscillating electric field and magnetic field traveling in space. And Heinrich Hertz in 1887 experimentally demonstrated electromagnetic waves. He demonstrated that by oscillating electricity and magnetism, you would get waves that behaved very much like light waves. Nowadays, we'd call what Hertz found radio waves. Well, turned out that was a whole era for finding all sorts of new waves. There were also infrared waves that were discovered just outside the red visible spectrum of light. There were ultraviolet waves, which were invisible waves discovered just outside the visible violet spectrum of light. And in 1895, Wilhelm Conrad Röntgen discovered a mysterious new form of radiation by accident, which he dubbed X-rays. And remarkably, after 2 short weeks of experimenting with X-rays, Röntgen took the first X-ray photograph of the human body, which is shown on the right. He used his wife Anna as a test subject and took a photograph of her hand. And you may wonder whether it's ethical or not to use your spouse in experimental testing, but it was a different era, I guess. Though it is said that his wife, when she first saw the image, said, "I have seen my own death." Well, the way that X-rays are generated is in what we call a cathode ray tube. Basically what you do is you take a mostly evacuated tube of glass and you create a huge electrical potential difference between a cathode and an anticathode. And if you create a really big electrical potential difference, the electrons will shoot off the cathode and they'll collide with the anticathode. And when they do, they produce X-rays. And I'll say a little bit more about this in a moment. But what happened in that era is people weren't really sure what to make of X-rays. What was their physical origin? People weren't sure. Were they a new form of particle? They acted very much like particles, which now that people had been convinced that light is a wave, it seemed very strange to think of X-rays as a new form of light because they acted like particles. It could be a new form of wave. Was it another? But people weren't sure whether it was a new type of particle, a new type of wave, or just another manifestation of electromagnetic waves like light and infrared and ultraviolet. And there were 3 properties of X-rays that seemed very unlike light and the other electromagnetic radiation that had been discovered. First of all, X-rays didn't seem to satisfy refraction when they entered a material. I've already mentioned that when you put visible light in glass or water, it changes direction. X-rays didn't seem to do that. Also, we know that light, when you reflect it off of a flat surface, it reflects in a single direction. If I shine a flashlight off a mirror, I get a single beam reflected. But when you reflect X-rays at a surface, you found that instead of the beam of X-rays being reflected in a single direction, they got reflected diffusely. That some X-rays went in all directions. And third, X-rays didn't seem to experience diffraction, which we mentioned earlier, this bending around corners. So they acted very unlike anything we had seen before. Well, into this came Charles Glover Barkla. I love that his name is Charles Barkla. I don't know if he played basketball or not. He was a British physicist who worked as a professor of natural philosophy at the University of Edinburgh. And his PhD advisors were J.J. Thomson, the person who discovered the electron, and Oliver Lodge, a key developer of wireless telegraphy, or as we would now think of it, radio. And he did most of his work on X-ray scattering, X-ray spectroscopy, measuring basically the colors of X-rays that we can't see but we can detect, and the excitation of secondary X-rays, which is what we'll talk about in a moment. He eventually won the Nobel Prize in 1917 for his work on X-radiation of the elements. So, at that point, I mentioned that X-rays didn't seem to act like other electromagnetic waves like light. Now, but people had already deduced and determined that light had polarization. It acted as a transverse wave. And so if the polarization of X-rays could be detected, that would be a good demonstration that X-rays must be another type of electromagnetic wave. But ordinary methods of polarizing light don't really work for X-rays. X-rays shoot right through ordinary polarizers. X-rays shoot through everything. That's why Röntgen was able to measure his wife's hand, because it goes right through. They go right through most everything. And there's another technique that people use to polarize light called using Brewster's angle, which means if you shine light or you reflect light at just the right angle off an object, the beam that gets reflected ends up being perfectly polarized. But because X-rays, when they reflect off an object, go in all directions, this idea of Brewster's angle doesn't work. However, researchers knew that X-rays, when they pass through a gas, they end up scattering and they produce secondary X-rays. And the way you can think about this in modern terms is, suppose you have an electron and you have an electromagnetic wave hitting that electron. Well, the electromagnetic wave is a transverse wave, so if the wave's going to the right, it's wiggling in this picture up and down. Well, when that electric field hits that electron, the electric field's wiggling up and down, so it causes the electron to wiggle up and down. And when that electron wiggles up and down, that's the way you also produce electromagnetic waves, is by wiggling electrons. So when that electron starts to wiggle, it produces a secondary X-ray. However, those secondary X-rays end up being strongly polarized because, first of all, picture that this red line indicates the X-rays going basically into the page, and they're unpolarized. So some of the X-rays wiggle up and down, some wiggle left and right. Well, those X-rays that are wiggling left and right, they produce X-rays that are horizontally polarized, that go up and down. Those X-rays that were originally wiggling up and down make the electrons wiggle up and down, and they produce X-rays that are vertically polarized and moving horizontally. So when that unpolarized beam goes into a gas, in the vertical direction you should see horizontally polarized light. In the horizontal direction you should see vertically polarized light, or X-rays in this case. Well, the thought of Professor Wilberforce, one of Barkla's colleagues, was, hey, suppose you take that polarized, you take now those X-rays, that secondary radiation, it should now be polarized. And so now you imagine you've got a polarized beam coming in. Well, that polarized beam now, it shouldn't produce any X-rays vertically, because when it excites vertical motions of electrons, it should only produce horizontal X-rays. And so you should also be able to, so those X-rays that come off in that secondary case is a good illustration of polarization. So in essence, he's saying you'd get a third beam of radiation. You have your primary unpolarized beam. You get a secondary beam that's polarized from scattering off of a gas. And if you scatter that secondary radiation off of a gas again, you should get this tertiary radiation. And if you measure that tertiary radiation, it'll tell you if you've got polarization or not. Unfortunately, that secondary radiation is very weak. That tertiary radiation would be negligible. You wouldn't see it at all. Well, this is where Barkla himself came up with a better idea. He realized that when X-rays are produced in that cathode ray tube, they must already be polarized right at that anticathode. That because those electrons are flying off of the cathode and hitting the anticathode. The reason we get X-rays in the first place is because those electrons are screeching to a halt. They're basically accelerating or deaccelerating horizontally. And when they deaccelerate horizontally, directly in the vertical direction, the X-rays produced directly vertically should already be polarized. which means we don't need to use a gas to first polarize the X-rays. Some of the X-rays coming right out of this tube must already be polarized. So if we collimate that, the secondary radiation should already show us polarization effects if X-rays can be polarized. And this is exactly what Barkla did. He put his cathode ray tube here. He collimated the light from it and had a tube of gas basically here. And this tube of gas would basically then scatter these secondary rays. And these secondary rays could then either be measured in a vertical direction or a horizontal direction. And he noted that, okay, suppose I've got the bulb horizontally, so the X-rays would be polarized horizontally. Well, then it's going to excite electrons horizontally in this box. And if I try and measure those over here, I won't see any X-rays here. But if I have the bulb oriented vertically, well, now the X-rays are going to are going to be vertically polarized. They're going to excite vertical X-rays that I will be able to detect here. So depending on whether the bulb is horizontal or vertical, I'll either see no X-rays here or X-rays here. And this is exactly what Barkla saw. As the bulb was rotated around the axis of the primary beam, there was no change in the intensity of the primary radiation. However, there was a considerable change in the intensity of secondary radiation in both the horizontal and vertical directions, one reaching a maximum while the other attained a minimum. By turning the bulb through a right angle, the electroscope, which had previously indicated a maximum, indicated a minimum, and vice versa. In short, the secondary radiation he saw demonstrated polarization. Barkla had quite conclusively demonstrated that X-rays must be another form of electromagnetic radiation, and a set that works very differently in many ways than light and ultraviolet and infrared. Well, the same year that Barkla demonstrated that X-rays have polarization was a big year for physics, because Einstein that year developed special relativity and explained the photoelectric effect by essentially repostulating that light is a particle form. The photoelectric effect, basically researchers had noticed that when light is shined on a metal surface, sometimes it ejects electrons from that surface. And nobody could explain how the wave nature of light could result in electrons being ejected from that surface in just the way it was being seen. And Einstein argued that the only reasonable way to explain that result was by assuming that light consists both as a stream of particles and as a wave. And this led to the development of quantum mechanics, and the quantum era of light began. And quantum mechanics was developed rapidly to explain the structure of atoms and the nature of light-matter interactions. And detailed studies, however, of the behavior of light particles, what we now call photons, was somewhat hindered by the lack of a quality light source. If you want to study the particle nature of light, you really need a good source of light, and ordinary light bulbs just wouldn't cut it. So a lot of the study in that early era was hindered by that. But one thing that happened in that era was Paul Dirac, a brilliant physicist, made a statement which became both famous and infamous. And that was his attempt to try and reconcile the particle and wave natures of light. In essence, people concluded very quickly, or the way they interpreted quantum mechanics early on is they said, well, we know that there's a wave associated with all particles now. Light and all matter has a wave nature to it. Light has a particle wave nature, matter has a particle wave nature. How do we interpret that wave nature now if we're talking about discrete particles? And the way we interpret it is as a probability. The wave tells you how likely it is to find your particles at one position or another. But Dirac further reasoned, and he said, well, in order to have though, if we can't have different photons interfering with each other, because if different photons could interfere with each other, then that would mean in some locations individual photons would have to annihilate to produce the low points in the interference pattern. And at other points, the photons would have to basically duplicate and produce the same amount of energy as 4 photons. And this would go against the conservation of energy. Well, the other way that Dirac said we have to look at it, he said, well, we can't have that happen. We can't have particles annihilating and creating spontaneously to produce the results. The only way we can interpret this is that an individual photon only interferes with itself. The wave properties of a photon are contained in that photon alone, and interference between different photons never occurs. Well, that was a very provocative statement. It was really based on philosophical arguments, and it was natural to ask whether we could test this somehow. Well, it would take some years to do because, again, we were lacking a quality light source. And in 1953, Charles Townes and his students produced the first microwave amplifier based on the principle of stimulated emission. And it was called a maser, microwave amplification by stimulated emission of radiation. Stimulated emission is basically the idea that if you've got an atom with extra energy in an excited state, it's possible for a photon to come along and make that atom release that energy as another photon. It's stimulated emission. The atom is stimulated to release light by the presence of other light. And this led, of course, to the laser in 1960 by Theodore Maiman. And Bazov, Prokhorov, and Townes shared the 1964 Nobel Prize for this discovery. Bazov and Prokhorov did other very important work in the theory. And with the laser's invention, we could do all sorts of experiments that couldn't be done before. And one of the geniuses in this sort of work is Leonard Mandel. He was born in Berlin, Germany, earned his PhD from Birkbeck College at the University of London in 1951. And he ended up becoming one of the pioneers of the field of quantum optics. And the idea of quantum optics is it's a study of really digging into the quantum nature of light. Most of optical science, even to this day, we can do most optical science by just treating light as a wave. We don't have to worry about that quantum aspect. But that quantum aspect studying that quantum aspect allows us to test the foundations of quantum mechanics itself. We can actually look at and say, what does quantum mechanics mean? And does it really mean what we think it does? And that was what Leonard Mandel's specialty was doing experiments to say, what is quantum mechanics? But of course, you may have heard the whole idea of quantum optics has now led to the possibilities of quantum computers, quantum cryptography, quantum teleportation. Leonard Mandel had a hand in all of these phenomenon. All of the ideas that are being talked about nowadays, Leonard Mandel influenced all of them. Well, I have some personal connection to him because he became a faculty member at the University of Rochester in 1964 at the invitation of his colleague and very good lifelong friend, Professor Emil Wolf, who was my PhD advisor. And in fact, I had an office across the hall from Leonard Mandel and got to talk to him a number of times. He was a really, really wonderful person. Now, one of the things that came up was this question again about interference between two photons. Now, when you think of the interference of light waves, the way that interference works is that the two waves have to have a definite relationship to each other. They both have to be oscillating or wiggling up and down in a definite way. For instance, you get complete constructive interference if both of them are wiggling up and down in sync. You get complete destructive interference if they're wiggling opposite to each other. One is at its peak when the other is at its low. Well, you can ask, one way you can think about interference of independent photons is to interfere two independent light beams together. You could take two lasers and shine them at the same spot on a screen, and you could ask, do you get interference fringes if you shine two lasers at each other? You point two laser pointers at the same spot at the wall. Do you get interference fringes? Well, you don't get interference fringes from the combination of those two lasers. And the reason for that is any laser still has some inherent fluctuations in it. And so those two lasers are going to fluctuate independently of one another. And on average, you're not going to see any interference because they don't maintain that definite relationship. They may both lasers may start wiggling in sync, both going up and down at the same time. But eventually, due to thermal effects, quantum effects, they eventually wiggle out of sync and back into sync and out of sync again. And on average, you're not going to see an interference pattern. But you'll notice I said on average. And you can ask, is the absence of interference just an artifact of the averaging process? Or is it really a true manifestation of Dirac's statement that interference between two photons never occurs? Because neither laser can produce an interference pattern by itself. So the question is, do they truly produce no interference, or are we just not seeing it? And here's the way Mandel thought about it. And this is a picture of mine. I drew here a picture of an idealized, perfect wave oscillating up and down perfectly. And here's another wave that we would call quasi-monochromatic. The black wave is a wave that's almost a single frequency, but it tends to drift, like I was talking about. And you can see from this picture that at one point in time, the two waves are in phase, they're wiggling up and down together. At another point in time, they're out of phase. So if we were to average over this entire time, we would say on average, they're not in sync. But if you look over a very short period of time, for instance, near this in phase region, you can see there are 5, 6, 7, or 8 wiggles where the two waves are completely in phase. So if instead of averaging over a very short period of time, or instead of averaging over a long period of time, if we manage to have a detector that can really just measure the interference pattern over a very small number of cycles, we might see that interference pattern. Well, this is exactly what Mandel and his colleague Magyar did in 1963. They took two independent lasers and they used a photodetector to basically put them in sync. And they used mirrors to combine the two lasers together and measure their interference pattern on the screen. And this coincidence unit could be used to basically gate and just record the interference pattern for a very small period of time. And I believe what they did is they actually sent pulses in. And so these photodetectors here measured the pulses. And when they saw a pulse, they said, okay, take a quick picture. And then we record that picture, which is just the interference pattern over a short period of time. And in fact, the incredible thing is they did see interference fringes. And this is an image directly of the camera, and it's very faint to see, but this dark pattern in the middle, you can see these vertical lines here. And if you look at a cross section of that pattern, they did see the characteristic up and down that indicated that, yeah, these two light beams were interfering with each other. So this original result was pretty incredible because it seems to indicate that Dirac's original statement was incorrect. Because Dirac's original statement was that different photons cannot interfere with each other. And here was an experiment that seemed to indicate that photons from independent lasers were producing interference. Or are they? This is where things get really weird and delightful. In 1967, Mandel and another colleague, Fligor, repeated this experiment but used very low intensity light sources. And by very low intensity light sources, you can say that with a very, very high probability, there was only one photon present at the detector at any time. So there was only ever one photon present in the system at any instant. And then they they basically did many, many trials and built up, because with one photon, you don't see any signal. So they then repeated this many, many, many times to calculate the average pattern that they would see in their detector. And they still found an interference pattern. So even only though one photon was going through the system at a time, they still found interference. And their conclusion, surprising as it might seem, the statement of Dirac quoted in the introduction appears to be as appropriate in the context of this experiment as under the more usual conditions of interferometry. And I note at the bottom, Dirac's statement is appropriate, but it's a very strange statement because this is a very strange result. Because not only is this saying that a single photon is producing this interference pattern, but the way it's producing this interference pattern is evidently this photon, the wave part of this photon is coming from the two lasers simultaneously. That the reason that we see an interference pattern with a single photon, with single photon measurements, is because the photon is in some sense coming from both lasers at the same time. And we get an interference pattern because we can't tell which laser it came from. And this was one of the many experiments that Mandel did, showing just how weird quantum mechanics is and remains at this day. Well, let me conclude here. This talk ended up being a little longer than usual because I tried to explain things more than I usually do. That we've now reached a new phase of optics as well. Sort of what I've been calling the modern era is we've now can do things with light that previously were thought to be impossible, like creating negative refractive index materials, like in the bottom left picture here, that we can actually create images with a flat piece of material in principle. We're still working out the details of it in practice. And of course, optical cloaking, which I've talked about in another talk. That the focus in optics in recent years, throughout history, the focus in optics has been, what is the behavior of light? And nowadays, the modern focus in many ways is, how can we make light do whatever we want it to do? Well, thank you for listening to this. I hope you enjoyed it. Here are some of the references I used for this particular talk, if anybody needs to look any of them up further. And let me remind you again, plug my own book, that my book on the history of falling felines is out there now. And hopefully sometime within the next year, my book on the history of invisibility will be out. Okay, thank you for listening.